Okay, hypothesis testing continued. Okay, so if you are curious about all the different things that we can actually hypothesis test for or even create confidence intervals for, a good place to go is page 359 in your textbook. Check out that table if you're interested to kind of investigate the different things that we could have talked about. My focus for you is going to be 3 of those things. So first of all, we've already talked about p-hat being used to help us predict or understand p, remembering that this right here is a population parameter. And remember that p-hat is usually called a test statistic, or actually a sample statistic. Or even a point estimate if you're doing confidence intervals. Some of the vocabulary, right? And then when we're thinking about proportions, you probably noticed when you looked at the output for, right here's the output for our hypothesis testing, that we're talking about that z-distribution that you all are very familiar with. It is a modified version of a z-score. And I think in class I actually gave you the formula. You do not need to do that by hand, but the concept is still similar. So we know that the test statistic here, that's the vocabulary, right? The test statistic that goes with that p-hat, when p-hat gets turned into, remember the Honey, I Shrunk the Kids thing, right? Into a normalized value, we like to use z, okay? And so we go to the z-distribution, all of this. Okay, so the next 2 types of hypothesis tests that I would like us to think about here at the end of the semester, we have X bar. We have the idea of some population mean, predicting or helping us understand the true population average. So again, sample statistic here, sample mean, right? Population parameter here. We're talking about average. This is the mean or the average of the group that we're predicting. Now, you may remember, I'm going to say recall here. You may remember that we did have a z-score that we used to use back in sampling distributions after the central limit theorem had kicked in. And the z-score looked something like this. Take your sample value, subtract that population value, assuming that we know it, right? And then we would divide by the population standard deviation divided by the square root of n. And we've had some discussion in class about the central limit theorem. We know things such as, we need a good enough sample size before using this technique of looking at grouped up data, before that's going to help give me something that is guaranteed to be normal. And we know it can be actually kind of hard sometimes to convert non-normal type relationships into something normal, even when we change the discussion from individual data to grouped up data, right? So a lot of statisticians will say things like, hey, if you don't already have a normal bell curve and you're trying to apply the central limit theorem, you definitely need at least a sample size of 30. Other statisticians will say, hey, if it's more extreme, you may need a sample size of 300 or 500, right? It can take a while to get this beautiful thing called the central limit theorem to fully kick into its full momentum, into full effect. And so while that's nice and that's great and everything, we do have some issues. You see, as we want to hypothesis test, as we want to run or create confidence intervals, we are usually trying just to predict one thing that we do not know. That one thing being the population average. Now maybe you're looking at this z-score formula and you're saying, well, wait a second, Ms. Barrier, I see mu and I see sigma. And if you are doing that, that's exactly what I want you to be doing, because right here is the problem, right there. The idea is we're focusing in this phase 2, in this discussion about predicting or making inferences about the mean, we're focusing on the mean, but yet if we don't know what that is, we probably don't know the actual variance or standard deviation. So it's like we're kind of taking a leap here, right? So what we end up doing, instead of using a traditional z-score, is we end up using something called t, which is very, very similar to a z-score. The formula actually only varies slightly. It does this, right? So instead of seeing the population symbol here, we will use what we have, again, because we're saying we probably don't know the truth. We will use our sample standard deviation. Now, you all probably know that we stats people are not very keen on estimating more than we have to, and we like to be very careful, especially when we start trying to make predictions. So in doing this, we do step away from that traditional normal distribution, but we find a friend that's pretty close, that plays pretty similarly. It's called the t distribution. And actually, this t distribution is so much like the z that it's going to be symmetric around mu of 0. It's going to have a standard deviation once you've, honey, I shrunk the kids, shrunk that data down, normalized it, of 1. And it's going to play mostly similar, except it will take into account your sample size with the degrees of freedom of n subtract 1. So the idea is this picture right here actually will change, starting off maybe up here, change, moving up and down, getting better and more close to that z distribution that we started with based on the sample size. You do not have to really know too much about this, just that it's kind of a derivative or a version of a z distribution, right? And the idea is, if you can imagine that thing going up or down, the tails will have, more area in them with a smaller sample size, right? Because then, of course, you would not want to pretend that it's that perfect z distribution. And putting area in the tails, by the way, we don't like, because we're using that center part of our bell curve to help create these confidence levels. Maybe in your mind you're thinking empirical rule, center 95%, right? Well, if you lift this thing up, you're not getting center 95% unless you go a lot more out, right, with this t distribution. So we will not get some of the same margins of errors. They'll be a little bit bigger sometimes if that sample size isn't good. It will change some of our values. But as far as you all are concerned, you will still continue to use StatCrunch. So I'm talking to you about something conceptual, but my hope for you is that you can say, oh, okay, that's cool, Miss Barrier, I'm moving on. I know that in StatCrunch I will choose T. Okay, that's what I'm hoping. So again, we have test statistic Z going on with the population parameter, which, by the way, you always choose proportion test in StatCrunch anyway, so you don't have to even think about the Z. And then down here when we're talking about mu, we're talking now about T as my test statistic. So we kind of change, just slightly change, graphs. And I say slightly because if that sample size is large enough, it's basically going to act the exact same way as a Z. This is just a safe way for us to approach this. So with the T, we will actually choose T-test in StatCrunch. Everything else, as far as the pictures, the shading, things like that I've already discussed, is going to be the exact same. So for you all, it's simply one different click in the computer. And your interpretations of that p-value will be the same, p-value being the probability of getting what you got in that sample, assuming what you've assumed for the truth, right? So that kind of dynamic remains. So we're going to start with that. Now, I do have one other thing that I want you to think about, because I really believe that as you go on from this class, I think you can go to page 359 and you can figure out all of these different other cool combinations if you want to. But we haven't talked any about how to handle categorical data. Things that are not numeric, where we can't just get that average or maybe even getting the percent in some certain case doesn't really help us much with what we're trying to look at, right? So categorical. This is especially maybe beneficial for some of you who are trying to add that bonus part to your assignment of making a confidence interval or a hypothesis test. Now, if you're using categorical data, and you're going to do what I'm about to teach you, this right here is going to be specific to contingency tables or two-way tables. So the way you will know that you are looking at what I'm talking about is when your data would kind of naturally or intuitively be stored as a two-way table. We are trying to look at this association between two variables, right? Maybe gender versus ice cream preference. I don't know, maybe how someone declares themselves politically based on how they voted, which candidate they voted for. Is there a link? Is there an association? So when we're looking at this, we really are curious about an association. But we're not really in that top section of this discussion, right? We're not really looking at the mean in this case. We're not really looking at the percent. We're simply saying, is there an association between these variables that are typically going to be categorical? So, you may have something like a two-way table where you have your numbers going on, right? Like, I don't know, maybe I have heart rate, high heart rate, low heart rate. Did this person go for a run? Did they not go for a run? Whatever it may be that I'm trying to link. And then I get some values, right? And I'm trying to say, is there a connection? Now remember, you also can see if there's a connection by simply going to some of the graphs and watching those patterns, right? We know here on the contingency tables that you can put explanatory on the row, and then you can look at the response as you take your eyeballs and scan across those columns using percentages. So you can already have a pretty strong feel for if there is an association. But we like to run a test, now that we're in this fancy inference section, right? We like to run a test called an independence test. This thing's pretty cool. Technology will take you the whole way here as long as you can handle the concept. But it's an independence test to say, hey, is there some sort of a relationship going on? Now in this case, I'm not going to talk to you in too much detail, but in this case what we are actually using is something called chi-squared. Okay. There's actually several tests that we can use chi-squared for. Chi-squared comes from a different picture, just like this T up here came from a different picture, and actually it starts off with 0 being on the left-hand side, and it starts to look kind of like that, where it's kind of all lumped over on one side. But then as n increases, the coolest thing ever happens. It also will become beautiful and bell-shaped for you. Again, conceptual, don't waste too much time considering this. So, as we're running these tests, just know that it's a very similar idea, right? Where we're still looking at the area, we're still looking at the p-value, similar kind of discussion, maybe just a different way of asking it. So what I want to do with you here is I'm going to run one hypothesis test with you, with the mean, and then we will talk about one independence test so that you've seen one example of each. Okay, so first starting with the mean. That should be the one that is most similar to what you have already watched when I was talking about proportions. Let's say we have an example here. An example about coffee. Okay, so we have this coffee machine. Maybe it's your Keurig at home, right? And it dispenses coffee into cups, okay? And the machine gives you some different values of what it's dispensing. I'm going to say it tells us, the machine says, apparently, dispenses 10 ounces, right? I say apparently because we haven't run the test yet. Okay, so we're told the machine dispenses 10 ounces of coffee every single time you put your coffee cup there. And we're curious about, the truth of that. So we go and we understand that anything, even machinery, right, will have some variance from time to time. So we say, let's explore this. Let's look at the true average amount of coffee that we should expect. So we took some actual values. We took 20. Actual amounts for 20 cups. We have 9.9, 9.9 again, 10.0, and 9.9, 10.0. Oh my, I have a lot of these. Okay, 9.7, 6. I think I actually have this in a spreadsheet. I'll try to pull this up in a second. So we have this huge list from our 20. Hopefully I'm going to write them all. From our 20 cups of coffee, okay? And the question is, is 10 ounces actually the true average of my machine, right? So what we can do, here, let's do this. Is there evidence that the machine is not giving us enough coffee? So similar to the proportion thing, we're going to go over to StatCrunch, but I think before we do that, let's make sure that we are clear on how we can set up a hypothesis test here. Remember the H0, HA. Remember that we said H0 will always have the equal sign, HA will always be the exact opposite, and it will have an inequality or a not equal sign. So let's see, is there evidence that the machine is shortchanging customers? So first we have to analyze what in the heck are we trying to prove, or what are we checking, right? Shortchanging customers. And remember before we also said with a hypothesis test, you will always use a population parameter, such as P or mu or something like that, right? You will always use that in H0, HA whenever we're dealing with these two scenarios. So I'm going to put my little mu here, and I'm talking about averages, not percents. Shortchanging customers. So what would that mean? Shortchanging would mean there's not enough, right? So shortchanging, less than, right? So if we're shortchanging customers, that would mean that the truth, this mu down here, is less than what we have been told. We've been told 10 ounces. So less than 10 ounces, right? And remember that H0, that always does have the inequality. It will go in the top. It's our assumption. The true opposite would look like this, greater than or equal to 10 ounces. But of course, because we're using it as that assumption, we will actually run the hypothesis test with an equality. Just in your mind, understand kind of what we're setting up here. And so the idea is, we do need to get that X bar. I don't know what that is yet. X bar equals what? And we're going to see what the probability of whatever these samples just now gave me, what's the probability of that happening if, in fact, this is the truth, that the average amount of coffee is 10 ounces. So now let's go over to StatCrunch and see if we can take a look at the kind of information that we would get. Let me see something. I think I have this stored. And so if you watch what I'm typing in, you're welcome to pull this up and try this example yourself. I kind of recommend that. It might help you have a better understanding. I went to Explore to find this. Oh, I spelled something wrong. SRA, chapter 20. Okay, so I'm going to go here. So we are focusing just on coffee, okay? Those values that I just now wrote up, they're already entered in. And I've actually changed the example some. Remember a second ago you had the summary, so you knew p hat right away. So I'm showing you a different version here. Stat. We know that we will choose proportion stats or t-stats most of the time. This is not a percent problem. It's not proportion. We will choose t-stats. This is a single sample. That's all that we are doing in this course. Now at this point, this is the different part I wanted you to see. We are not looking at a summary because you actually have the original data, right? So we will say with data. It doesn't change a lot. You just don't put in the summary information. You tell StatCrunch where to go find the numbers. So it's under coffee. And we could actually create a confidence interval. We will in a second. First, let's do this hypothesis test. So let's see, what did we say? We said 10, I think, ounces is what we're checking. And we're checking to see if we're getting ripped off. So are we actually getting less than 10 ounces? So again, you put in the number, it will match, and then you change your inequality sign for HA. This should be super easy and fun for you. The big stuff's when you have to interpret. So we get this right here basically for free. No. Okay. This is what we just now got, right? So again, identifying things that you should know. Our X bar is this value right here, showing a sample mean. So had you chosen to add up these numbers above and get your own average, that's what you would have had. You're welcome for me doing that faster. We talked a second ago about the T distribution needing degrees of freedom. We had a sample size of 20, so we're not surprised to see DF at 19. It's in subtract 1. Our t-statistic, remember this is called my test statistic, it's the one it actually cranked through on its normalized picture. We have a t equal to 3.49. Again, most of this is if you're just a visual person, you want to see that picture. What you all are focusing on, I'm still drawing you a picture, but what you're focusing on for your solution is that p-value, right? So, p-value, the probability of this right here happening, assuming that this right here is true, right? The probability of us getting an average coffee amount of 9 8/10, assuming that 10 ounces is the true average. Could this have happened with 20 cups of coffee? Okay, so the p-value here. Alpha, we said we will default to a 5% level of significance, understanding that we can change that strictness as needed. But usually we're defaulting to 5% unless you're told otherwise. And again, in this example, p-value is less than 5%. This tells us to reject H0. Again, remember that your two outcomes would be reject H0 or fail to reject H0, right? That's the only two things that you can say at this technical stage. Then you interpret things into words that other people might understand, right? So reject H0. Let's look back up here at the hypothesis, or hypotheses, okay? So we just threw this one away. Remember, you can only ever prove HA, all right? And you're proving at your level of significance that you just ran the test at. With H0, you can go back to the previous video. Remember, with H0, you are never proving. With HA, you actually get to prove. So with H0, if we had not been able to reject H0, we would have failed to reject it. All we would have said is, hey, I can't dispute that, right? But we are having a good day. We are here. We rejected H0. So we get to say, at a 5% level of significance, there is evidence to prove that this coffee maker is ripping us off. Right, so we got to prove this one. And that's it. Again, if you're a picture person, which I am, and I told you I would draw you a picture, this is what you were looking at. You had your assumption of mu equals 10. You had what you found, which was over here, an x bar equals 9.845. And this right here is a left tail test, so your p-value was coming on the left-hand side right there. So that probability under the curve would have been this right here. That was your likelihood of finding that, or more extreme. Again, remember that frog example. This is very similar. The only difference is in the frog example, we used a z because we knew the standard deviation of the population. Everything else matches so closely that you should feel pretty good right now. Again, refer to the information I told you about how to know when to reject or not reject. Okay, so there's one example with the average. Now, if you're dying to see a confidence interval on this, it takes only a few more seconds. Let's go do that. We know from before that we always will get the same answer. I mean, I guess if you change your significance with one and it's right on the edge, it might be different, but generally it's going to match. So stat, still t-stat, still one sample, still with data. Everything is in coffee. And this time I'll choose confidence interval. And actually, since we're using an alpha of 5%, I really should use 90% here. So I'll do that just so you can see that you are able to change that confidence interval if you want. 95 is actually more popular, but just to make the two tests actually truly match. And there we have it. I hit compute. It was that fast. Okay, where can I put this? Let me put it up here. I want you to see both of these close together. Okay. Okay, so looking at this right here, notice there's your confidence interval. Pretty much as for free as the one down below, right? But this right here, the way you would interpret it is, hey, look, my confidence interval at 90% for the true average amount of coffee that we're getting from this machine, so I'm using population symbol here, comes out of the interval. We have 9.77 ounces to 9.92 ounces. So that's the prediction that we have. And again, we're going to see the same thing, right? If we're looking to say, hey, is there evidence the machine is shortchanging the customers? That was our question. Well, when you look at the confidence interval, please notice that 10 ounces is nowhere in that confidence interval. So again, we're saying, hey, you know what, that something looks a little bit off here, because we had assumed, or even when we weren't assuming, we were told, right, that 10 ounces should be the truth. So it's not in that interval. Either way, you would reject that idea. You would say that's probably not happening. Okay. So let me show you an independence test really quickly. I only gave you a few of these, but they're just so cool I couldn't leave it off because I think you'll really appreciate this. Now, with an independence test, it's basically like we're looking between different variables and we're trying to find an association. Now this independence test is actually, it's restricted to only 2 variables. If you ever found yourself in a situation where you had more than 2 things that you were comparing, you would need a different test, okay? So this right here, please note, this is just for 2 variables. Okay? And it plays so well. I mean, literally any time you run a hypothesis test for independence, you actually even get to use words, right? H naught will always be, well, I like to say it's always yes, whatever it is you're testing. So for example, yes, they are independent. And HA will be, no, they're not. And I'm wording it this way because if you do ever decide that you love statistics and want to study more, that yes-no mentality whenever you're dealing with words, I think that will get you pretty far. So yes for H naught, no for HA. And by the way, remember what independent even means, right? So here we're saying yes independent or yes not related. For HA, not independent would mean, okay, they are related. I know that's weird to have to consider that the interpretation like in regular language, but again, I think yes, no will take you further if you ever come back to this. So yes, no, there we have it. And on this example that I'm going to go through with you, let's say that we are looking at, what shall we look at? How about sex and opinion about banning cell phone use while driving? Let's see if there's some link between gender and people thinking cell phones should not be used while driving. Okay, so let's see, we have gender, we have sex here. Female, male. And then we have people who do not like, let's see, the idea of banning cell phone use by drivers. And then we have the ones who are in favor of banning cell phone use while driving. And these are the tallies. This is how many came up in each group. Or the frequencies, we might call it, right? Okay. Okay, and we know with the two-way table, if you were calculating things by hand, you might be inclined to put the totals, right, in the column and the rows at the end, and you may even be inclined to make some percentages. Go back to your notes for that. That's some good stuff, especially when you're trying to look for associations without a full test, without a full hypothesis test. For this right here, we're going to go to StatCrunch and actually run this full test of the yes-no for independence. Again, H naught and HA, anytime you're running an independence test, will always follow this format, where yes is the assumption and no, for whatever you were asking, is always going to be the alternative. And technically it is a chi-square test. So let's see. In StatCrunch, first of all, I'm going to need a new StatCrunch. Let's put this information in. I'll put the variable one will be gender or sex. So we have female.
You guys already good with your food, right? Take a
Right behind?
Oh man, I lost it. Okay. And we have male. And then we have opposing this banning of cell phones. And we have favoring this opposing, or yeah, the banning of cell phones. And again, the counts, we had 37. Oops, 46. 68. And 37. This may look familiar to you all, those of you who have used contingencies on your project. Okay, so let's go check this out. We're going to go to Stat, choose Tables. You know where to go. It's a contingency situation, so we'll choose contingency. And here we have a summary, so we'll say with summary. Okay, so the column, that was oppose and favor. The row was found in sex, right? The gender part. Okay, and it already defaults, see here, for hypothesis tests, chi-square test for independence. So I will leave that there and compute. That's literally how fast it is. Let me take a picture of this and put it in your notes. So again, we go to table. We choose contingency. And we run the test. I mean, you have to choose, I guess, the column names and the row, where the row names are found. But these are so quick that really it's a free 5 points on your exam if you choose to do this, or on your project. So p-value right there. You already had your H naught HA, so all you have to do is you say, okay, well, the probability 0.0056 of this occurring, assuming that yes, they are not related, or yes, they are independent, right? That's the probability of that occurring. And my strictness level, again, we will default it to 5%. So we get to see lots of rejecting today, don't we? That's not always the case, so don't be too happy about that. Okay, but we are going to reject H naught again. And that means we do throw this away. And we get to say, hey, these are not independent. It does look like gender is related to people's opinion about cell phones being banned while driving. So that's our conclusion, that we would actually tell someone at the end. Okay, I think this is definitely enough to get you all started having some fun.